This very short video outlines a quantitative risk analysis for a structure in an avalanche path. That structure could be for a power line, or it could be a ski lift tower, or it could be the top station of a ski lift as we see here, or it could be the building for a lift operator. It's important to note that a quantitative risk analysis is just one part of a risk assessment. Quantitative risk analysis is sometimes useful for planning assessments, but sometimes it's just too slow or too expensive. And quantitative risk assessments are rarely used for operational work. We're going to consider a structure exposed to a slope hazard such as avalanches, but it would apply to other kinds of slope hazards. So risk is the combination of the probability of the event, often P sub h, but here it's P sub a, the exposure, which I'll denote by an S, and the vulnerability V. When these three variables are independent, then we can multiply their average values or expected values to get risk. And we're going to consider multiple scenarios, such as avalanche size. We can choose our scenarios however it helps to solve the problem. It could be a dry avalanche and a wet avalanche, a powder avalanche and a dense flow avalanche, but here I'll use the destructive size scale. We're going to organize our risk calculation as a table, and it's important to note that we're dealing with the expected or average values in this table. In the left-hand column, we see the scenarios, and we've chosen to use the destructive potentials. So a size D2 avalanche, a size D3 avalanche, and a size D4. And let's assume that this path does not produce a size D5 avalanche, and we don't care about the size D1 avalanche because it doesn't really affect the tower. In the next column, we see the annual probability of the specific avalanche reaching the tower. So for a size D2 avalanche, it's 0.5. In other words, they reach the tower but once every second year. A size D3 avalanche will reach the tower about once every 10 years, so its annual probability is 0.1. And the size D4 avalanche is expected to reach the tower but once every 20 years, so its annual probability is 0.05. In the next column here is exposure, and the structure is in the middle of the path, so it's exposed for all these avalanches here. This variable gets a whole lot more interesting if we're dealing with people or vehicles moving underneath an avalanche path. The vulnerability is the fraction of loss. For a size D2 avalanche, it doesn't do any damage. A size D3 avalanche will do about 10% damage to the structure, and a size D4 avalanche will destroy the structure. Now we can calculate the risk for each of these avalanches by multiplying the annual probability times the exposure times the vulnerability. So for a size D2 avalanche, 0.5 times 1 times 0 is 0. For a size D3 avalanche, 0.1 times 1 times 0.1 is 0.01. And for a size D4 avalanche, 0.05 times 1 times 1 is 0.05. Now it might be tempting to add up the three numbers in this column to get the total annual risk to the structure, but it turns out we have a little more work to do, and I'll show you that in these next two columns. Now to calculate the total risk, we need to adjust the annual probabilities for the scenarios with less frequent avalanches. For the size D4 avalanches, we have an annual probability of 0.05. There are no less frequent avalanches, so after adjustment, that is still 0.05. Now for the D3 avalanches, we do not want to include the risk due to the less frequent avalanches that occur but once every 20 years. So we take this 0.1, subtract the 0.05, and we get 0.05 for the adjusted annual probability. Similarly, for the D2 avalanches, which occur about once every 2 years, we do not want to include the risk due to the D3 and D4 avalanches. So we take the 0.5, we subtract these two 0.05s, and we get 0.4 for the adjusted annual probability. Now we can multiply the exposure, 1, times the vulnerability of 0 for size D2 avalanche, and the adjusted annual probability of 0.4, and we get a total risk contribution for the size D2 avalanches of 0. For the size D3 avalanches, we have our exposure of 1, our vulnerability of 0.1, adjusted annual probability of 0.05, so contribution towards the total risk is 0.005. For the D4 avalanche, exposure 1, vulnerability 1, adjusted annual probability 0.05, and we have 0.05 for the adjusted risk due to the D4 avalanches. Now we can add up the numbers in this column here to get 0.055 as the total annual risk to the tower from snow avalanches. Now, if you're interested in more information on the total risk calculations, here are two references. You can press pause and write them down. Now we can also express the three scenarios from the table as a risk graph. These are normally log-log plots, But in this case, to spread the points out, I've shown the vulnerability along the x-axis on a linear scale. Nevertheless, we still have low risk in the bottom left corner and high risk in the top right corner. On the y-axis, we have the annual probability of impact, which is just the annual probability of the avalanche times the exposure, which is always 1. On the right-hand y-axis, we have the return period of impact. So for an annual probability of 1, we have a return period of impact of 1. For an annual probability of impact of 0.1, we have a 10-year return period of impact. And for an annual probability of impact of 0.01, we have a return period of impact of 100 years. And here we have the dots for the 3 scenarios, D2, D3, and D4. For the size D2, we have a vulnerability of 0 and annual probability of impact of 0.5. For the D3, we have a vulnerability of 0.1 and an annual probability of impact of 0.1. For the D4, we have a vulnerability of 1 and an annual probability of impact of 0.05. Now this graph and the preceding tables have shown average or expected values. However, if we look at the D3 scenario, there are some times when it could cause more than the expected damage, and sometimes when these avalanches might cause less. Similarly, we might see a shift towards more frequent avalanches or towards less frequent avalanches. And we are particularly interested in the upper right corner because that contributes to increased risk. One of the ways of calculating these uncertainties is a Monte Carlo simulation, and that is the subject of a subsequent video. A few key points from this short video. Risk analysis is just one part of an assessment as described in ISO 31000. Quantitative risk assessment is rarely used for operational assessments. It's just too slow and often too expensive. And even for planning assessments, we only sometimes use a quantitative risk assessment. Risk can be considered as having 3 components: the probability of the event, here P sub A, the exposure, and the vulnerability. When these are defined independently, we can multiply them together to get the risk. To solve a lot of problems, we need to consider more than one scenarios, and in this example, we used 3 classes of avalanche magnitude or size. When we do calculate the total risk, it can be compared with the risk due to other activities, which is really quite valuable. Thanks for watching.